Okay, so finally we finish section 4.5, Sullivan's Precalculus. The last video here, we discuss objectives 6 and 7, having done 5 in the last video, solving polynomial equations. Two theorems, one having to do with bounds on zeros, how large can they be, how great can they be, and how lesser can they be, and the intermediate value theorem. First, bounds on zeros. So here's a strange theorem, which I guess is, well, it rivals the other theorem that we used to have on bounds on zeros in Sullivan for weirdness. Let f denote a polynomial function whose leading coefficient is positive. Big M greater than 0. Okay, so positive number, big M, is a real number. And if the third row in the process of synthetic division, in other words, when you do the synthetic, you've got 3 rows, the coefficients, and you got another row, and you got the line, and then, here's the third row, 1, 2, 3. If the third row contains only numbers that are positive or 0, then big M is an upper bound on the zeros of f. That means there is no 0 that's greater than big M. On the other hand, if you have little m negative, that is less than 0, a real number, and if this third row of f by x minus m, that means m is in the loft, right, contains numbers that alternate positive or 0 and negative or 0. So they alternate non-negative and non-positive. Then little m is a lower bound to the zeros of f. There is no 0 that's less than little m. Okay, so if we, let's see, use the bounds on theorem to find upper and lower bounds to the zeros of f. Okay, so from example 4, we have these rational zeros, and to find an upper bound, start with the smallest positive integer that is a potential rational 0, which is 1. And then we're gonna go up from there, 1 to 2 to 3, well, to 6, and that's it. Subsequent positive integers, if necessary, until an upper bound is found. To find a lower bound, start with the largest negative integer, negative 6, that is a potential rational 0. Largest negative, negative 1. There's potential rational 0, that is negative 1. And then we'll try negative 2, negative 3, negative 6 until a lower bound is found, until we get one of these strange lines in the third row of the synthetic. Well, if you do all these synthetics, this is what you see for these various numbers. Okay, for example, you do the 1 and you run the synthetic, and what do we have? We have positive, 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 and 0. Positive, 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 and 0. And that tells us that we have an upper bound, which is 1. There is no 0 for f of x, which is greater than 1. Okay, because we had all non-negative numbers in that third row of the synthetic. Okay. Now, starting at -1 and going greater, that is greater in absolute value. What do we get when we do the synthetic every time? Okay, now what are we looking for? Alternating non-negative and non-positive. So we had, when we tried -1, we had non-negative and another non-negative. So that's not alternating. Then the next time we have same thing, a non-negative number 2 and another non-negative number 7. So that's not going to be alternating the way that is required. Same thing happens again. Now we're going through the potential rational zeros. We get to -6 and we have non-negative, non-positive. Okay, this is promising. But then in the third row of the synthetic, we have another non-positive. So it's not going to be alternating the way it needs to be. And so -6 is not even a lower bound. So -7 will be considered the lower bound. For r equal 1, we saw what happens. Since the third row of the synthetic for r equals -7 does result in alternating values, we know that -7 is a lower bound. So we went to the next lower integer, and we did get non-negative, non-positive, non-negative, non-positive. We did get that alternation that we were looking for. So we conclude that there are no zeros less than -7. In other words, -7 is a lower bound on the zeros, however many or few there are for this function f of x. Notice that in looking for bounds, 2 zeros were discovered. These zeros are 1 and -6, because we had the 0 remainder. The division went evenly for those two numbers. If you were going to climb a mountain or a hill that's 1,000 feet high, would you at some point be 500 feet off the ground? Well, if you think about it, yeah, you realize you have to be 500 feet off the ground at some point, because, you know, if you're going to start at ground zero on the ground, and then you're going to end up 1,000 feet above the ground, you know, we can't just you know, blip our way from 400 to 600 without crossing 500. Well, this is kind of what the intermediate value theorem is saying. You've got a polynomial function, meaning it's continuous. You can graph it without lifting your pencil from the paper. And you've got a less than b, and if f of a and f of b are of opposite sign, then you're going from a negative to a positive. You got to cross 0 at some point. That's what the x-axis is, the line y equals 0. So a problem that you possibly would see at some point, it looks like this. Show that this function has a 0 between 1 and 2. Well, if you think about it, has a 0 between 1 and 2. And so what we're going to do to determine that is find f of 1 and find f of 2. That's the a and that's the b. And we do get 1 negative and we get 1 positive. And that pretty much shows it, okay? that means that we're going to have a picture that looks like this, right? This, if things, you know, this is not drawn to scale, but this could be 1, -1 for the right scale. And this point over here could be 223. You know, we could tweak the scale so that it worked out like that. Well, that means that there is a 0 somewhere between 1 and 2. That would be the 1 and that would be the 2. And so by the IVT, there has to be a 0 between 1 and 2. That's guaranteed by the theorem. So we have shown it. Why? Because we had opposite signs. Well, what we could do is narrow down this interval with tighter and tighter, a tighter and tighter band in the vertical, I should say in the horizontal. You know, if we consider vertical lines, creating a tighter and tighter band around this 0 to determine what it is. And so basically the idea is just to continue to find two numbers that are such closer and closer together, such that you get a negative and a positive, just the way we did when we were showing that f had a 0 between 1 and 2. And I believe this is what the calculators do when you use a 0 feature in the calculator. And this is what we see here for the f of x that we were given. Here's the 0, or represented by an x-intercept, between 1 and 2. Here's a decimal approximation, not the exact, but an approximation to that 0. And I believe the calculator uses this method of narrowing the band. It wouldn't be a bisection method. I think it was describing taking 1/10 every time. But that is kind of the traditional way to approximate, for example, zeros.